Hello Professor, this is Kamajaman from Zhongguang Kim Lab. Now I am going to make a YouTube video for the final exam. In this video, I will explain some problem about final exam. Problem 1, 2, 3, 4, 5 and 6. So now I am going to solving this problem. So let's start. This is the first problem. First problem has only one question. This question is draw the arrow according to the below condition. So there are some conditions, so we need to draw the arrow. So detection of the diffusion flux cannot affect the polarity of electron and hole just from high to low. So detection of drift flux can affect the polarity of electron by E field. By E field detection due to charge. Current for electron only flows the reverse direction due to charge. So I can just make this arrow which is the polarity electron and hole just from high to low. So I make this all arrow like this way. So now I am going to solve the problem number 2. This is problem 2. There is maybe two questions. So first question is draw energy band diagram for accommodation, depletion, inversion mode using MOSFET, which is a p-type semiconductor. So I draw this energy band diagram for accommodation, depletion and inversion mode using MOSFET. So accommodation, majority carrier, there is this is insulator, this is p-type semiconductor. This is for accommodation, depletion and inversion. Accommodation, majority carrier accumulated under the gate. Majority carrier accumulated under the gate. So then depletion is normally on. Depletion is normally on. Then inversion, minority carrier accumulate under the gate. Same things like accommodation. This is the majority. This is the minority. Minority carrier accumulated under the gate. Question number 2. How to remove the conductive channel at VGS equal 0 volt as shown below figure. So I am just showing this figure how to remove the conductive channel at VGS equal 0. Positive charge induced in metal gate. Negative charge accumulate under the gate terminal. Consequently, p channel vanish. So these types of way can remove the conductive channel at VGS equal 0. Problem number 3. Explain the mechanism why the current shows constant at saturation region. So I write here I just explain here why the current shows constant at saturation region. In the saturation area, the MOSFET serves as a continuous current source. This is such that the gate and drain voltage no longer have control over the current flows. After raising BDS to a point where pins of force, therefore the current is virtually constant beyond that value of BDS. If BDS equals 0 and BGS greater than BTS, BGS greater than BTS, a conductive channel is opened between the drain and source. Drain and source when BDS is increased, current flows across the channel. If BDS exceeds BGS minus BTS, then the channel will be closed near the source region. This is the refer to the pins of regime. Past this point, increase in BDS cause a proportional increase in resistance because the channel close off even further away from source region. As a result, the current does not appreciably increase as BDS increase. That is the reason why the current is saturated. So that was problem theory. First question. Problem theory question number 2. Draw the energy band gap, equilibrium and saturation mode of MOSFET. It is most important things for know better about MOSFET. So equilibrium, no gate or drain, to source voltage applied at DC equal to gate voltage equal drain voltage equal 0. Equilibrium Fermi level are aligned from S to D via channel semi. No current at equilibrium, gate voltage equal drain source equal 0. So energy band gap for equilibrium mode like this way, you can draw this way. Then situation, if BTS greater than 0 volt, enhancement drain voltage saturated when it is saturated, then equal BGS minus BTS. If BTS less than 0 volt, depletion mode, BTS saturation equal BGS minus BTS. When BD greater than BDS, then the MOSFET goes on saturation mode. Energy band gap for saturation mode of MOSFET. So this energy band gap for saturation mode of MOSFET. So you can compare with this. This is the MOSFET and this is MOSFET. This is the mode of MOSFET for equilibrium, and this is for saturation mode. This is the question 3 for problem 3. Why is transconductance GM in saturation region is affected by BGS, not BTS? Transconductance GM in saturation region. So MOSFET act as a constant current source in the saturation region. This is the because after increasing BDS to such a level that pinch occurs, the gate and the drain voltage loss its control over the current flowing. So beyond that value of BDS, the current is almost constant. This is problem number 4. Question number 1. What is the difference between acceptor like state and acceptor level EA? So bad for conductance and do not contribute to the conduction. It is created in MOSFET. This is the metal oxide semiconductor, and this is for P type unionized acceptor, ionized acceptor. Acceptor level contribute to the conduction and good for conductance. It is the form in P type semiconductor. Problem 5. Explain what causes threshold voltage rule of phenomena. The decrease of threshold voltage with decrease in gate length is a well-known short channel effect called the threshold voltage rule of. As the channel of the device is reduced to nanoscale region, the charge distribution in the channel is influenced by the field organizing from the source drain. You can explain these things. This is substrate doping and this depletion aids shear BTS rule of phenomena. You can show this way. So this is the question number Question 2 for problem 5. Explain the mechanism of low BTS in terms of charge sharing. This is short channel MOSFET, long channel MOSFET. In short channel device, high longitudinal E field is dominant and carries move with saturated velocity in the channel. Big two differences for short channel against long channel. At this time, since the charge is formed in the channel with negatively charged donor ions, the voltage is sufficient to form a channel without a large gate voltage. This is question number 3 of problem 5. If BTS become low and minus BTS, what is going on the MOSFET? Describe the problems. So, as a result, as channel length BTS shift in negative direction, this BTS shift in negative direction, as a result a device with a short channel has a lower threshold voltage. It demonstrates that device with smaller geometries have larger drain current at the same gate to source voltage. How to reduce hot carrier effect and DIBL? This is question number 4 for problem 5. How to reduce the hot carrier effect and DIBL? One of the most effective ways to control the hot carrier effect is to include a field reducing region in the transistor structure. This region is called LDD, means lightly doped drain. Lightly doped drain is the short name is LDD, or MDD, moderately doped drain. Reduce the amount of damage a device suffers and consequently increase its operational lifetime. Increase substrate doping concentration, reduce oxide thickness, hollow doping. So this is the hollow doped region using implantation, and there is explain how one of the most effective ways to control the hot carrier effect to include a field reducing region in the transistor structure. This is the question number 5 for problem 5. What are the pros and cons for LDD and hollow? LDD pros: reduce hot electron degradation. Cons: resistance increase with LED, which leads or power dissipation. Hollow reduce the DIBL effect, increase device fabrication complexity. This is problem 6. This is about describe about impression for this class. What was the impression of my class? Actually, I cannot explain what benefited for these courses. I was very worried about these courses because I was very weak. So after finish some classes, I learned many things and I can clear many ideas about semiconductor physics. So I want to give thanks a lot to professor for explain briefly and explain nicely and physically. So all of students and they learn very confidently. I think that in future we can develop a lot if we continue study this subject, like how professor taught us. And what are the takeaways for these courses? This means what things we learn more during these courses. Actually, this is for semiconductor physics. So semiconductor was the most important thing for electronics. Peter went up semiconductor we learn in intermediate school level also, but we did not remember after many years. So now can remember what professor teach us. So another thing is thermodynamic distribution function, energy band diagram, carrier concentration, tonal level and export level, compensated semiconductor, drift current and diffusion MOSFET. So everything is most important. Every topic is very essential for us, especially for who want to learn, who want to be electronics engineering. So it's most important things. So I want to give thanks again to our professor that teach us very nicely, and thank you so much.